Medical physics for you.
Hello everyone. Welcome to another lecture. Today we are going to continue our discussion about the measurement of ionizing radiation. In the previous video we briefly discussed the introduction of the ionizing dose measurements, exposure, and electronic equilibrium. Today we will discuss the basic quantities and definitions that are essential to understand the measurements of ionizing radiation. Like photon fluence, energy fluence, KERMA, CEMA, absorbed dose, and stopping power. Let us start with the fluence. If there is a monoenergetic ionizing radiation beam, this beam can be described by the following quantities: particle fluence, energy fluence, particle fluence rate and the energy fluence rate. Particle fluence. The particle fluence is the number of ionizing particles, dN, incident on a sphere of cross-section area dA. Energy fluence. The energy fluence is the number of ionizing particles with energy dE incident on a sphere of cross-sectional dA. The energy fluence can be written in terms of the particle fluence as follows. The particle fluence rate and the energy fluence rate is the particle fluence and the energy fluence divided by the unit time respectively. All the previous are for the monoenergetic beam. But as discussed before in the X-ray production lecture, the generated photon beam is not a monoenergetic beam. It is a spectrum of photon energies. In the case of polyenergetic beam, the particle fluence and energy fluence become particle fluence spectrum and energy fluence spectrum respectively. Look at this figure. This figure shows the photon fluence spectrum and energy fluence spectrum for an X-ray beam with kVp of 250 kV. If you look at the photon fluence spectrum curve, you can see that the fluence increases with increasing energy until it reaches the peak, then the value decreases. This curve tells the number of photon particles with specific energy that cross a sphere with cross-section dA. For example, the number of photon particles that has 100 kV is higher than the number of the particle with 200 kV. The energy fluence is the number of the particles multiplied by their energy. The question now is, why do we need to study the fluence? Simply, it is important to well understand the fluence and understand the attenuation coefficients, that we talk about in the lecture 2, to be able to understand how the KERMA and absorbed dose is calculated, as we will discuss in the next lecture. Now there are two questions for you to answer. 1. Why there is no photons below 50 kV? 2. What these two spikes represent. Try to answer these two questions yourself. The answer will be at the questions section at the end of this video. KERMA. KERMA is an acronym for kinetic energy released per unit mass. When an indirectly ionizing radiation, like photon or neutron beams, fall into a matter, the energy of this indirectly ionizing radiation is imparted to the matter into two steps. Step 1. The indirectly ionizing radiation transfers its energy to release a secondary charged particles, i.e. electrons, either by photoelectric effect, Compton effect, or pair production. Step 2. The released secondary charged particle transfers its energy to the medium through ionization and excitation. Step 1 is known as KERMA. So, KERMA is the mean energy transferred from the indirectly ionizing radiation to charged particles in the medium per unit mass. The unit of KERMA is joule per kilogram, which known as Gray. CEMA. CEMA is the acronym for converted energy per unit mass. As we mentioned before in previous videos, when a directly ionizing radiation, like electron, alpha, and proton beam, falls on a matter, it loses its energy by interaction with the medium's atoms via electromagnetic force interactions and cause ionization and excitation to these atoms. This converted, or in other words, this lost energy from the directly ionizing radiation to the medium called CEMA. So, CEMA is the energy lost by the incident charged particles, in collision in a mass dm. CEMA also is measured by the gray. Absorbed dose. Absorbed dose is a very common term in radiotherapy, so, it is important to understand the meaning of the absorbed dose in a medium. Secondary charged particles are produced in the medium, either due to step 2 in the indirectly ionization radiation or due to energy loss by directly ionizing radiation. These secondary charged particles transfer some of their kinetic energy to the medium. This imparted energy to the medium called absorbed dose. The secondary charged particles can also lose some of their energy in form of radiative losses, Bremsstrahlung, or annihilation. If these charged particles dissipate their energy outside the medium, these are not counted as absorbed dose. So, absorbed dose is the mean energy imparted by ionizing radiation to matter of mass, m, in a finite volume, v. The unit of absorbed dose is gray. It is important to note that, the released electron, deposits its energy along its track while traveling in the medium. So, the absorbed dose does not take place at the same point as KERMA. Stopping power. We briefly mentioned the stopping power in the interaction of ionizing radiation with matter lecture. Here we will discuss in further details. The linear stopping power is the rate of energy loss per unit mass of charged particle. The mass stopping power is the linear stopping power divided by the absorbing medium density. Dividing by the density eliminate the dependence of the mass stopping power on the absorbing medium density. As we have mentioned before, the released electron can lose their energy either by collision with atomic orbital electrons or by generating X-ray via Bremsstrahlung effect. So, the types of stopping power can be collision or radiative. The collision can be soft collision, where a small amount of energy is transferred to the absorbing medium atom, or hard collision, where a significant amount of energy is transferred to the absorbing medium atom. The mass stopping power proportional to the inverse square of particle velocity. That is mean, when the particle velocity decreases, the rate of energy transferred to the medium increased. That is why there is a Bragg peak in the proton beam as discussed in the previous lecture. The mass stopping power proportional to the square of particle charge. That is mean the stopping power for the massive charged particles like alpha particle is higher than the tiny ones like electrons. This is why the alpha particle range is too small compared to the electron. The mass radiative stopping power is proportional to the square of the absorbing medium atomic mass. That means the Bremsstrahlung effect probability increase with increasing the absorber atomic number. That is why the high atomic number materials like tungsten is used as a target in the X-ray tubes. Sometimes, in case of the hard collision, the released electron might have enough energy to release another electron. The secondary released electron can be from the same atom or from different atom. These released electrons that cause further ionization called delta rays. So, these delta rays can dissipate its energy away from the originally incident electron. The unrestricted stopping power considers all collision events, regardless of the amount of energy transferred in a single interaction, which include the energy transferred through soft, hard collisions and delta rays. On the other hand, the restricted stopping power focus only on the localized energy deposition. So, the concept of the restricted stopping power is introduced to calculate the energy transferred to a localized region of interest. For example, if we concern only in the dose, i.e. the energy transferred to the medium, in localized area, we will ignore any electron escape this area and dissipate its energy somewhere else. That means, if an electron transfers some of its energy within that localized area and by somehow a delta ray generated, there is a threshold energy that if exceeded the delta ray will escape the area. This threshold energy depends on the localized area or the region of interest that we need to calculate the dose in. For problems involving ionization chambers, a frequently used threshold value is 10 kV. The range of a 10 kV electron in air is of the order of 2 mm. So, for the restricted stopping power, any collision where the transferred energy to any individual electron is higher than the threshold value will be ignored in the calculations. Imagine, we want to calculate the absorbed dose within this localized area. The threshold energy to escape this localized area is delta 1. So, any delta ray that have enough energy to escape this localized area, i.e. its energy more than the threshold energy, won't be calculated. If our focus increase and the localized area increase, the threshold energy increase accordingly. So, the restricted stopping power now will be restricted only to focus on all ions that have energy less than the threshold value of delta 2. Now, it is time for some questions. Question 1. In this figure, why there is no photons below 50 keV? As we discussed in the X-ray production lecture, the produced X-ray is a spectrum that has energies from 0 to maximum applied tube volt. To remove the small energy photons that can be easily absorbed in the body during scanning, the filters are applied. So due to presence of filters in the X-ray tube, the photons with small energy will be absorbed and won't reach the body. This called beam hardening. Question 2. In the same figure, what these two spikes represent? These spikes represent the characteristics X-rays that produced in the X-ray tube target. For more information, please refer to the X-ray production video. That is all for today's lecture. Thank you.